An optical fiber is a flexible, transparent fiber made by drawing glass or plastic to a diameter slightly thicker than that of a human hair. Optical fibers are used most often as a means to transmit light between the two ends of the fiber and find wide usage in fiber-optic communications, where they permit transmission over longer distances and at higher bandwidths than wire cables. Fibers are used instead of metal wires because signals travel along them with lesser amounts of loss. In addition, fibers are also immune to electromagnetic interference, a problem from which metal wires suffer excessively. Fibers are also used for illumination, and are wrapped in bundles so that they may be used to carry images, thus allowing viewing in confined spaces, as in the case of a fiberscope. Specially designed fibers are also used for a variety of other applications, some of them being fiber-optic sensors and fiber lasers. Optical fibers typically include a transparent core surrounded by a transparent cladding material with a lower index of refraction. Light is kept in the core by the phenomenon of total internal reflection, which causes the fiber to act as a waveguide. Fibers that support many propagation paths or transverse modes are called multimode fibers, while those that support a single mode are called single-mode fibers. Multimode fibers generally have a wider core diameter and are used for short-distance communication links and for applications where high power must be transmitted. Single-mode fibers are used for most communication links longer than 1,000 meters. An important aspect of a fiber-optic communication is that of extension of the fiber-optic cable such that the loss is brought about by joining two different cables is kept to a minimum. Joining lengths of optical fiber often proves to be more complex than joining electrical wire or cable and involves careful cleaving of the fibers, perfect alignment of the fiber cores, and the splicing of these aligned fiber cores. For applications that demand a permanent connection, a mechanical splice which holds the ends of the fibers together mechanically could be used, or a fusion splice that uses heat to fuse the ends of the fibers together could be used. Temporary or semi-permanent connections are made by means of specialized optical fiber connectors. The field of applied science and engineering concerned with the design and application of optical fibers is known as fiber optics. History. Guiding of light by refraction, the principle that makes fiber optics possible, was first demonstrated by Daniel Colladon and Jacques Babinet in Paris in the early 1840s. John Tyndall included a demonstration of it in his public lectures in London. 12 years later, Tyndall also wrote about the property of total internal reflection in an introductory book about the nature of light in 1870. When the light passes from air into water, the refracted ray is bent towards the perpendicular. When the ray passes from water to air, it is bent from the perpendicular. If the angle which the ray in water encloses with the perpendicular to the surface be greater than 48 degrees, the ray will not quit the water at all, it will be totally reflected at the surface. The angle which marks the limit where total reflection begins is called the limiting angle of the medium. For water, this angle is 48 degrees 27, for flint glass it is 38 degrees 41, while for diamond it is 23 degrees 42. Unpigmented human hairs have also been shown to act as an optical fiber. Practical applications, such as close internal illumination during dentistry, appeared early in the 20th century. Image transmission through tubes was demonstrated independently by the radio experimenter Clarence Hansel and the television pioneer John Logie in the 1920s. The principle was first used for internal medical examinations by Heinrich Lamm in the following decade. Modern optical fibers, where the glass fiber is coated with a transparent cladding to offer a more suitable refractive index, appeared later in the decade. Development then focused on fiber bundles for image transmission. Harold Hopkins and Narinder Singh Kapani at Imperial College in London achieved low-loss light transmission through a 75 cm long bundle which combined several thousand fibers. Their article, titled "A Flexible Fiberscope Using Static Scanning," was published in the journal Nature in 1954. The first fiber-optic semi-flexible gastroscope was patented by Basil Hershowitz, C. Wilbur Peters, and Lawrence E. Curtis, researchers at the University of Michigan, in 1956. In the process of developing the gastroscope, Curtis produced the first glass-clad fibers. Previous optical fibers had relied on air or impractical oils and waxes as the low-index cladding material. A variety of other image transmission applications soon followed. In 1880, Alexander Graham Bell and Sumner Tainter invented the photophone at the Volta Laboratory in Washington, D.C. to transmit voice signals over an optical beam. It was an advanced form of telecommunications, but subject to atmospheric interferences and impractical until the secure transport of light that would be offered by fiber-optical systems. In the late 19th and early 20th centuries, light was guided through bent glass rods to illuminate body cavities. Junichi Nishizawa, a Japanese scientist at Tohoku University, also proposed the use of optical fibers for communications in 1963. As stated in his book published in 2004 in India, Nishizawa invented other technologies that contributed to the development of optical fiber communications, such as the graded index optical fiber as a channel for transmitting light from semiconductor lasers. The first working fiber-optical data transmission system was demonstrated by German physicist Manfred Borner at Telefunken Research Labs in Ulm in 1965, which was followed by the first patent application for this technology in 1966. NASA used fiber optics in the television cameras that were sent to the Moon. At the time, the use in the cameras was classified confidential, and employees handling the cameras had to be supervised by someone with an appropriate security clearance. Charles K. Cow and George A. Hockham of the British company Standard Telephones and Cables were the first to promote the idea that the attenuation in optical fibers could be reduced below 20 decibels per kilometer, making fibers a practical communication medium. They proposed that the attenuation in fibers available at the time was caused by impurities that could be removed, rather than by fundamental physical effects such as scattering. They correctly and systematically theorized the light loss properties for optical fiber, and pointed out the right material to use for such fibers: silica glass with high purity. This discovery earned Cow the Nobel Prize in Physics in 2009. A crucial attenuation limit of 20 decibels per kilometer was first achieved in 1970 by researchers Robert D. Maurer, Donald Keck, Peter C. Schultz, and Frank Zimmer working for American glass maker Corning Glass Works, now Corning Incorporated. They demonstrated a fiber with 17 decibels per kilometer attenuation by doping silica glass with titanium. A few years later they produced a fiber with only 4 decibels per kilometer attenuation using germanium dioxide as the core dopant. Such low attenuation ushered in the era of optical fiber telecommunication. In 1981, General Electric produced fused quartz ingots that could be drawn into strands 25 miles long. The Italian research center CSELT worked with Corning to develop practical optical fiber cables, resulting in the first metropolitan fiber optic cable being deployed in Torino in 1977. CSELT also developed an early technique for splicing optical fibers, called spring groove. Attenuation in modern optical cables is far less than in electrical copper cables, leading to long-haul fiber connections with repeater distances of 70 to 150 kilometers. The erbium-doped fiber amplifier, which reduced the cost of long-distance fiber systems by reducing or eliminating optical repeaters, was co-developed by teams led by David N. Payne of the University of Southampton and Emmanuel de Cervera at Bell Labs in 1986. Robust modern optical fiber uses glass for both core and sheath, and is therefore less prone to aging. It was invented by Gerhard Bernsey of shot glass in Germany in 1973. The emerging field of photonic crystals led to the development in 1991 of photonic crystal fiber, which guides light by diffraction from a periodic structure, rather than by total internal reflection. The first photonic crystal fibers became commercially available in 2000. Photonic crystal fibers can carry higher power than conventional fibers, and the wavelength-dependent properties can be manipulated to improve performance. Uses. Communication. Optical fiber can be used as a medium for telecommunication and computer networking because it is flexible and can be bundled as cables. It is especially advantageous for long-distance communications, because light propagates through the fiber with little attenuation compared to electrical cables. This allows long distances to be spanned with few repeaters. The per-channel light signals propagating in the fiber have been modulated at rates as high as 111 gigabits per second by NTT, although 10 or 40 gbit per second is typical in deployed systems. In June 2013, researchers demonstrated transmission of 400 gbit per second over a single channel using 4-mode orbital angular momentum multiplexing. Each fiber can carry many independent channels, each using a different wavelength of light. The net data rate per fiber is the per-channel data rate reduced by the FEC overhead multiplied by the number of channels. As of 2011, the record for bandwidth on a single core was 101 TBit per second. The record for a multi-core fiber as of January 2013 was 1.05 petabits per second. In 2009, Bell Labs broke the 100 times kilometer barrier. For short-distance application, such as the network in an office building, fiber-optic cabling can save space in cable ducts. This is because a single fiber can carry much more data than electrical cables such as standard Category 5 Ethernet cabling, which typically runs at 100 mbit per second or 1 gbit per second speeds. Fiber is also immune to electrical interference. There is no crosstalk between signals in different cables, and no pickup of environmental noise. Non-armored fiber cables do not conduct electricity, which makes fiber a good solution for protecting communications equipment in high-voltage environments, such as power generation facilities, or metal communication structures prone to lightning strikes. They can also be used in environments where explosive fumes are present, without danger of ignition. Wiretapping is more difficult compared to electrical connections, and there are concentric dual-core fibers that are said to be tap-proof. Fibers are often also used for short-distance connections between devices. For example, most high-definition televisions offer a digital audio-optical connection. This allows the streaming of audio over light using the Toslink protocol. Advantages over copper wiring. The advantages of optical fiber communication with respect to copper wire systems are broad bandwidth. A single optical fiber can carry over 3 million full duplex voice calls and 90,000 TV channels. Immunity to electromagnetic interference. Light transmission through optical fibers is unaffected by other electromagnetic radiation nearby. The optical fiber is electrically non-conductive, so it does not act as an antenna to pick up electromagnetic signals. Information traveling inside the optical fiber is immune to electromagnetic interference, even electromagnetic pulses generated by nuclear devices. Low attenuation loss over long distances. Attenuation loss can be as low as 0.2 decibels per kilometer in optical fiber cables, allowing transmission over long distances without the need for repeaters. Electrical insulator. Optical fibers do not conduct electricity, preventing problems with ground loops and conduction of lightning. Optical fibers can be strung on poles alongside high-voltage power cables. Material cost and theft prevention. Conventional cable systems use large amounts of copper. Global copper prices experienced a boom in the 2000s, and copper has been a target of metal theft. Security of information passed down the cable. Copper can be tapped with very little chance of detection. Sensors. Fibers have many uses in remote sensing. In some applications, the sensor is itself an optical fiber. In other cases, fiber is used to connect a non-fiber optic sensor to a measurement system. Depending on the application, fiber may be used because of its small size, or the fact that no electrical power is needed at the remote location, or because many sensors can be multiplexed along the length of the fiber by using different wavelengths of light for each sensor, or by sensing the time delay as light passes along the fiber through each sensor. Time delay can be determined using a device such as an optical time domain reflectometer. Optical fibers can be used as sensors to measure strain, temperature, pressure and other quantities by modifying a fiber so that the property to measure modulates the intensity, phase polarization, wavelength, or transit time of light in the fiber. Sensors that vary the intensity of light are the simplest, since only a simple source and detector are required. A particularly useful feature of such fiber-optic sensors is that they can, if required, provide distributed sensing over distances of up to 1 meter. In contrast, highly localized measurements can be provided by integrating miniaturized sensing elements with the tip of the fiber. These can be implemented by various micro and nano fabrication technologies, such that they do not exceed the microscopic boundary of the fiber tip, allowing such applications as insertion into blood vessels via hypodermic needle. Extrinsic fiber optic sensors use an optical fiber cable, normally a multi-mode one, to transmit modulated light from either a non-fiber optical sensor or an electronic sensor connected to an optical transmitter. A major benefit of extrinsic sensors is their ability to reach otherwise inaccessible places. An example is the measurement of temperature inside aircraft jet engines by using a fiber to transmit radiation into a radiation pyrometer outside the engine. Extrinsic sensors can be used in the same way to measure the internal temperature of electrical transformers, where the extreme electromagnetic fields present make other measurement techniques than possible. Extrinsic sensors measure vibration, rotation, displacement, velocity, acceleration, torque, and twisting. A solid-state version of the gyroscope, using the interference of light, has been developed. The fiber-optic gyroscope has no moving parts, and exploits the Sagnac effect to detect mechanical rotation. Common uses for fiber-optic sensors includes advanced intrusion detection security systems. The light is transmitted along a fiber-optic sensor cable placed on a fence, pipeline, or communication cabling, and the return signal is monitored and analyzed for disturbances. This return signal is digitally processed to detect disturbances and trip an alarm if an intrusion has occurred. Optical fibers fibers are widely used as components of optical chemical senses and optical biosenses. Power transmission. Optical fiber can be used to transmit power using a photovoltaic cell to convert the light into electricity. While this method of power transmission is not as efficient as conventional ones, it is especially useful in situations where it is desirable not to have a metallic conductor, as in the case of use near MRI machines, which produce strong magnetic fields. Other examples are for powering electronics in high-powered antenna elements and measurement devices used in high-voltage transmission equipment. Other uses. Optical fibers have a wide number of applications. They are used as light guides in medical and other applications where bright light needs to be shone on a target without a clear line of sight path. In some buildings, optical fibers route sunlight from the roof to other parts of the building. Optical fiber lamps are used for illumination in decorative applications, including signs, art, toys and artificial Christmas trees. Swarovski boutiques use optical fibers to illuminate their crystal showcases from many different angles while only employing one light source. Optical fiber is an intrinsic part of the light-transmitting concrete building product, lintricon. Optical fiber is also used in imaging optics. A coherent bundle of fibers is used, sometimes along with lenses, for a long, thin imaging device called an endoscope, which is used to view objects through a small hole. Medical endoscopes are used for minimally invasive exploratory or surgical procedures. Industrial endoscopes are used for inspecting anything hard to reach, such as jet engine interiors. Many microscopes use fiber-optic light sources to provide intense illumination of samples being studied. In spectroscopy, optical fiber bundles transmit light from a spectrometer to a substance that cannot be placed inside the spectrometer itself, in order to analyze its composition. A spectrometer analyzes substances by bouncing light off and through them. By using fibers, a spectrometer can be used to study objects remotely. An optical fiber doped with certain rare earth elements such as erbium can be used as the gain medium of a laser or optical amplifier. Rare earth doped optical fibers can be used to provide signal amplification by splicing a short section of doped fiber into a regular optical fiber line. The doped fiber is optically pumped with a second laser wavelength that is coupled into the line in addition to the signal wave. Both wavelengths of light are transmitted through the doped fiber, which transfers energy from the second pump wavelength to the signal wave. The process that causes the amplification is stimulated emission. Optical fiber is also widely exploited as a nonlinear medium. The glass medium supports a host of nonlinear optical interactions, and the long interaction lengths possible in fiber facilitate a variety of phenomena, which are harnessed for applications and fundamental investigation. Conversely, fiber nonlinearity can have deleterious effects on optical signals, and measures are often required to minimize such unwanted effects. Optical fibers doped with a wavelength shifter collect scintillation light in physics experiments. Fiber-optic sights for handguns, rifles, and shotguns use pieces of optical fiber to improve visibility of markings on the sight.